The hyperparameters of a random forest can be divided into two categories. The first category is the one that controls the predictive power of the model, or in other words, we can tweak the learning efficiency of the model by tweaking these hyperparameters. So the first one is n estimators. This is the number of trees the algorithm builds before averaging the prediction. So if we increase this hyperparameter, that means we are increasing the number of trees used by the algorithm to learn the dataset. The second one is max features. Now this is just simply the number of features or number of maximum features a decision tree can use to train on. And the third one is mini sample leaf, which is the minimum number of leaves required to split for an internal node. So that means the minimum number of records that it should have to be split further into the next level of the decision tree. So this is the first category of the hyperparameters using which we can tweak the predictive power. The second category is the one which helps us to tweak the speed or the performance of the model. So the first one in that one is n jobs, which is just the number of jobs or the number of CPU cores that the model can use to train on the dataset. So the default value is one, which is it will just be trained on using a single core of the processor, and it will not do any parallel computation. And if we set it as minus one, so that means that there are no limits to the usage of CPU cores, and it can take to however much are available to it. The second hyperparameter in this category is random state. Using this, we can tweak the randomness of the sample. If we give it a value, for example 10, and then we can use the same value to get the same results every time. And if we want to change the results of the model, then we can maybe set it up as 11 or 12. Just changing the number will change the randomness of the selected sub data sets for each decision tree, therefore changing the randomness for the whole model. The third one being OOB score. So OOB stands for out of the bag. Here, if we give the OOB as some set value, then the random forest, what it does is it takes one third of the sample and consider it as a validation data set. So that will not be used to train the model, and that will be just used to validate or evaluate its performance after training. Hence the term out of the bag sample. So these were all the hyperparameters for the random forest. Hello everyone. Now we are going to learn about random forest. So random forest is a supervised machine learning algorithm that can be used for classification and regression problems. Since it is based on decision trees, so decision tree scores would be a prerequisite for this one. And it is the first ensemble model that we are going to learn. So more about ensemble models on the next slide. Ensemble models are quite easy to understand. So ensemble simply means combining multiple models. And random forest is a great example of that. As the name suggests, random forest is a combination of multiple decision trees. And on the next slide, we'll try to understand ensemble models a little deeper. There are two types of ensemble modeling. The first one is bagging. Random forest is an example of this one. So bagging is simply just taking multiple subsets of the training data set and then training multiple weak learners on it. And the final prediction output would be a majority voting of all of the outputs of the weak learners. So there will be multiple decision trees, each trained on a subset of the training data set, and their output would be voted out, and the will result in the final prediction of the complete ensemble model, which is random forest. The second type of ensemble modeling is boosting, in which we take multiple weak learners and then we train them sequentially to create a strong learner. Here we are trying to improve the accuracy of the next model by taking the mistakes of the previous model. So ADA boosts and XG boosts are example of boosting in simple modeling. Now let us check bagging a little bit more detail. So bagging, which is also known as bootstrap aggregation, is an ensemble technique used by random forest. So here what we do is we take the whole data set and we split it into random samples. Then we train an individual model on those random samples, and at the end we take their majority voting for the final result of the aggregated model. Now the final majority voting is also known as aggregation here. So for example, suppose we have a data set of about 10,000 records. So here, for this example, we will train 10 small models on it, be those decision trees, on 1,000 records each, randomly selected from those 10,000 records. Now each decision tree will be trained on 1,000 record, and suppose for a single record, six decision tree, it taking it as a classification problem. So six decision tree are giving it as class A, and four decision trees are giving it as class B. So the majority voted would be class A as the aggregated result of the whole ensemble model. And that is how basically a decision trees based on decision tree based random forest works. So looking at the random forest algorithm, we have k number of records in the whole data set. We will take n random records to create our smaller subset of the data set. Then we will train individual decision trees on those random samples. For the output, we will take either majority voting or the averaging of all those individual decision trees based on whether the problem is a classification or a regression problem. And that is how a random forest algorithm is set up. Now, looking at some important features of random forest. So, since we are training individual trees on the subsets of the dataset, so each tree is different from the other one, hence the diversity come into play. So that's the first important feature of random forest. Second one is immunity to dimensionality. Now, since we are giving a subset of the dataset, or in other words, a small set of features instead of the whole feature set to each decision tree, therefore the trees do not have to be trained on large number of dimensions or large number of features. Third one being parallelization, since we'll be training the trees individually, and once the decision does not impact the other one, so those can be trained in parallel, and hence parallel computation can be done, which will help us to save some time and memory. Fourth one is the train to split. Now, since each decision tree will be getting a subset of the dataset and not the whole, so we do not even need to split the dataset into train and test. And the final one being stability, because our final output is either a majority voting on an averaging of the decision trees, individual decision trees outputs. Hence, we are getting the stability, and these are the important features of a random forest. Now, taking a look at the data set that we will be using for the implementation of random forest. Here we are using the Boston housing data set, in which we have about 13 features regarding the condition of the houses, or let's take a quick look at a few for example. So the first one is CRIM, which is per capita crime rate by the town, and the fifth one is NOx, which is nitric oxides concentration. So these are a few features regarding the houses, and using this data set, our target is to figure out the prices of the houses. So we have about 506 records in this dataset, and 13 features. And yeah, that is there for this dataset that we all need to know. Now we will quickly prepare the data set. So we are taking the features in the x variable and the output in the y variable, and then we are also using sklearn, that is scikit-learn's library, and using it to split our data set into training and testing subdata sets by a ratio of 0.33 for the test dataset size. And after that, we have the shape for our x and y datasets, which is 506, 13 and 506, 1. So that's how we will prepare the dataset for modeling. So finally, we are at the implementation of random forest. Here we are setting up a regression model based on random forest. We are setting up the hyperparameters as below. So the random state is 42. Now, whenever we use this random state and we use the same data set and the same other hyperparameter values, then we will get the same result every time. But if we tweak the random state even a little bit, then it will give us different result because of the randomness of subset collection for each decision tree in the random forest. The second hyperparameter is an estimator, so that is 1024, and the max feature is zero point 0.6. So, like this, we have defined the hyperparameters for the random forest regression, and then we will just quickly fit it or train it over the training dataset, and then we will make our prediction using predict method over the testing dataset. At the end, we are comparing the prediction scores of the x test and the y test and getting the mean square error from the predictions, which is coming out to be 10.681. So this is a quick way to implement random forest regressor. Now we will try to display the predictions on a scatter plot. So here we will be using the subplot method from matplotlib's library, and we'll be plotting our prediction points over the widget ones. So the points falling on the line or falling close to the line are the ones that are predicted without or with a smaller amount of error, and the ones that are falling away or have some distance from the line, those are the ones which have quite significant error for the predictions. Another important feature of random forest is variable importance. Now, as the name signifies, we can use random forest to get the importance of each and every variable or every feature that we have in the dataset. So here, what we'll do is we'll create a list of the feature name first, and then we will create a tuple of the variable with their importances. The importances will be given out using the random forest, and as you can see below, we are getting all the importance of every feature with corresponding to its name as well displayed below. So here, as we can see, LSET and RM have the highest feature importance of 0.35 each, and whereas the lowest one is of ZCHAS, which is 0.0015. So these feature importance can be used to even perform some feature selection, and we can all even use a smaller amount of features and maybe try those features out with some other model. So that's another way in which we can use a random forest. Continued from the last slide, here we'll try to visualize the feature importance using a bar chart. So we will be using matplotlib inline method, and then we will be just plotting the feature importance calculated. So as talked earlier, RM and LSAT have the highest, that is 0.035, and now it's much easier to visualize them and interpret them. As we can see here, ZN and CHES have the lowest one, which was close to 0.00. So that was all there is to know about random forest. Now we can just summarize the advantages and disadvantages of it. So the advantages are a lot, as you can see. We can use it for both classification and integration. We can even solve the issue of overfitting since it is taking majority voting on averaging based on the output of the randomized subset of the dataset. So it will definitely not overfit as it introduces randomization. The third one is it performs well even if the data contains null or missing values because the decision trees are always taking a subset of the dataset, so they are not they are quite robust for missing data. The fourth one is since each decision tree is independent, so we can use parallelization and the efficiency of the model will also improve. The fifth one is it is highly stable since we are just taking the average of the number of trees. The sixth one is we have the diversity here since each decision is individual and it will be different. Now, as discussed earlier, it is also immune to dimensionality since we are just giving a subset of the features to the decision trees. And in the eighth one, we do not even need to segregate into test and train since it is already taking 30% of the data in since it is already taking 30% of the data in cross-validation dataset. Now the disadvantages are quite few but important one, and they may be important for the decision of selecting this as your model of preference. So the first one is that it is quite complex since it is comparing between multiple decision trees, and here it since it includes so much randomness, so you may be unable to explain the decision quite well to your superiors. And the second one being the training time is more compared to other models because of its complexity. So that's true since you are creating so many decision trees here. Even if you use parallelization, if the hardware is not that efficient, then it will still take some time to make its predictions. So with this, we are at the end of the random forest.